Welcome back to the deep dive. So if you're trying to learn pretty much any branch of science right now, you definitely know the feeling. There's just so much stuff, it feels impossible to master it all.
Oh, absolutely. No single person can know all of physics. Not even close.
It's just too vast.
But, there's this really profound insight, especially in classical physics, that means you don't actually have to solve every single problem from scratch. There's like a universal knowledge hack, if you will.
And that's exactly what we're diving into today. We're looking at this concept called electrostatic analogs.
Right.
The core idea is, well, pretty simple but powerful. If you really nail the solution to one specific, maybe complex problem in electrostatics, say, mapping voltage around some weirdly shaped conductor,
Uh-huh.
that same solution instantly gives you the answers to maybe 3, 4, even 5 totally different problems. Things involving heat or fluids or even how structures bend.
We're basically tracking a single mathematical fingerprint. It shows up all over the place in the physical world.
A mathematical fingerprint, I like that.
Yeah, and that fingerprint is the Poisson equation. Understanding that equation is like the ultimate shortcut to seeing connections everywhere. It's fundamentally about how sources, things creating influence, generate potential fields around them.
Okay, let's unpack this a bit. Why electrostatics? Why does that field get to define this universal math?
Well, it's partly because the fundamental laws for static electric fields are incredibly pure, very clean. You really only need two main conditions.
Two conditions, yeah.
Yep. First, you've got the sources, the electric charges. These create the field, right? And we measure that using Gauss's law, basically. Field lines flow out from positive charges and into negative ones.
Okay, sources.
Got it.
What's the second condition?
The second is about the shape of the field itself. In electrostatics, the field has to be smooth. Mathematically, we say it has zero curl.
Zero curl. Okay, that sounds important. Can you give us a simpler picture of what a zero curl field actually looks like?
Sure. Think about gravity on a landscape. There are no whirlpools or eddies in a gravitational field, right? It just points downhill. A field with zero curl is like that non-swirling, non-vortexing.
Okay.
And because it doesn't curl back on itself, it means you can define your position within that field using just a single number, like your altitude or height on that landscape. That height map is the electrostatic potential, usually written as 5 to wall.
So the electric field vector, the force,
Yeah.
is just pointing downhill on that potential landscape.
Exactly. The field is simply the negative gradient, the steepness and direction of the downhill slope of that potential.
Right.
And here's the beautiful part. When you combine the law about the sources, Gauss's law, with this rule about the field's shape, the zero curl, everything simplifies. It collapses down into one equation.
The Poisson equation.
Poisson equation, yes. Nabel-2 per root against the Nabel-2 price salon dollar. It just says that the way the potential curves in space, that's the Nabel-2 curve phi part, is directly tied to how much source charge is right there. And what's really fascinating, as you said, is that this exact mathematical form, this relationship between curvature and source density, is about to pop up again and again.
Everywhere. You weren't kidding. Okay, let's see it in action. First stop. Heat flow. Thermodynamics.
Perfect example. Let's think about steady state heat flow. So energy moving through, say, a chunk of metal, but the temperature pattern isn't changing over time.
Right.
We can define the heat flow as a vector, math DFE she. It points in the direction the heat energy is moving, and its length tells you how much energy is flowing.
And the analogies just click into place, right?
They really do. The temperature, $2 at any point in the material. That's the direct analog of the electrostatic potential.
Temperature's potential.
What about sources? A source of heat, maybe like a small embedded radioactive pellet, constantly generating heat. That's the perfect analog for an electric charge.
Makes sense.
Yeah.
And the physics law governing the flow.
It's called Fourier's law of heat conduction. And mathematically, it's basically the twin of how we define the electric field from potential.
How so?
Fourier's law says that heat always flows from hotter regions to colder regions. It runs downhill on the temperature landscape. And the rate of flow, the vector math BA, is proportional to how steep that temperature hill is.
So math BFE is proportional to the negative gradient of $2.
Exactly. Mach BFE is just the thermal conductivity of the material. Compare that to Mach BFE, see the similarity.
Wow, okay, so if heat flow is proportional to the negative gradient of temperature, just like the E field is the negative gradient of potential. And you also have conservation of energy, which acts like Gauss's law.
You got it. You combine those, and for steady-state heat flow, you end up with an equation that is mathematically identical to the Poisson equation for electrostatics. Nabel-2 T is tech source strength, K Gal.
The consequence is huge then.
Massive. If you solve a tricky boundary problem for temperature distribution, you have simultaneously solved the exact same boundary problem for the electrical potential. You just swap the labels.
The source material gives a great example. Finding the heat flow between two long concentric cylinders. Imagine an inner pipe at temperature $2 and an outer pipe at T2
Right, a standard heat transfer problem. You solve for the temperature, $2 in the space between them.
and the solution involves the natural logarithm of the ratio of the radii. Like
That's the one. Now take that exact mathematical function, the one with the logarithm describing temperature. You keep the math, but you replace temperature difference with voltage difference, and you've instantly found the electrostatic potential fire between two cylinders forming a cylindrical capacitor. The heat flow calculation gives you the capacitance calculation for free.
That is, yeah, an incredible economy of thought. Just solve it once.
Precisely.
Okay, that's flow. Let's pivot. How about something completely static? Structural mechanics. You mentioned a stretched membrane.
Yes, this is chapter 12-3 in Feynman. Think of something like a drum head, or maybe a thin rubber sheet stretched really taut over a frame. Now, instead of energy flowing, we're looking at physical displacement. If you push down or pull up on this membrane with some external force per unit area, it's called $phi, then the vertical displacement of the membrane at any point, how far it moves up or down, let's call it 2, that displacement phi becomes the physical analog of our potential fire.
So height is potential, and the force filer we're applying.
That acts like the source term, the charge density.
Okay. How does the math work out?
Well, you have to analyze the forces on a tiny little square piece of that membrane. The external force phi pushing it up must be exactly balanced by the net downward pull from the surface tension in your curved membrane.
Right, it has to be in equilibrium.
Exactly. And when you write down that force balance condition mathematically, looking at how the curvature of the membrane relates to the tension and the external force, guess what equation you get?
Don't tell me.
Yep. You land right back on the Poisson equation. F2 equals EIA2F2. The curvature of the displacement is proportional to the applied force density.
Okay, now here's where it gets really interesting. According to the source, this wasn't just a theoretical connection.
Not at all. This was practical engineering back in the day, before we had powerful computers for simulations.
What did they do?
They would literally build these things, stretch a rubber sheet over a frame. If they wanted to model conductors at fixed voltages, they'd pin the edges of the sheet at specific heights.
Okay.
Then, where they wanted to represent positive charges, they'd use little rods to push up on the shape. For negative charges, they'd pull down. The amount they pushed or pulled was proportional to the charge strength.
Then way.
Yes. And then, to find the electrical potential in some point in space, they'd simply take a ruler and measure the physical height allers of the rubber sheet at the corresponding location on the model.
They were using the rubber sheet as an analog computer for electrostatics.
Exactly. Solving complex E&M boundary value problems by measuring the shape of a deformed membrane. It's incredibly clever.
That really shows the ingenuity before digital tools took over. Amazing.
Okay, speaking of flow, let's cycle back to things moving. How about particle diffusion?
Like neutrons spreading out.
Yeah, imagine you have a source, maybe in a nuclear reactor core or just some radioactive material, emitting neutrons into a surrounding medium, like graphite or water.
Okay, neutrons spreading out.
We track the density or concentration of these neutrons, let's call it nonolars, in a steady state where the pattern isn't changing.
Let me guess. Nonolac acts like the potential Neller.
You're getting the hang of this. Yes, the neutron density dollars is the analog of potential, and the strength of the neutron source, neutrons emitted per second per volume, that's the analog of the charge density hollers.
And because diffusion is driven by concentration gradients.
Right. Particles tend to move from high concentration to low concentration. When you write down the math for steady-state diffusion, considering the sources, surprise, surprise.
Poisson again. Vol.2 n at e sub h SDD, where d is some diffusion constant.
Spot on. So all that knowledge about electric fields around charges, it immediately tells you how neutron density should look around a neutron source. Same mathematical map governs both.
It's the same spatial pattern. Okay, now you mentioned fluids earlier. Let's refine that. Ideal fluid flow.
Yes, this takes us to a slightly simpler but maybe even more elegant case. The Laplace equation, which is just Poisson's equation in a region with no sources. Vol.2 equals $0.
So in electrostatics, that's just space without any charges. What does no sources mean for fluid flow?
For the specific case we're looking at, ideal, incompressible, irrotational fluid flow no sources is built into the setup.
Okay, break those down. Incompressible.
Means the fluid density doesn't change, like water, essentially. You can't really squeeze it. Divergence of velocity is 0.
And irrotational.
That's the key one here. It means the fluid isn't swirling locally, no little whirlpools or vortices. Mathematically, the curl of the velocity vector math BFE is 0. A nabla times math BFE is 0.
Zero curl again, just like the electrostatic field.
Exactly. And just like 0 curl for math BFE allowed us to define the scalar potential feat, 0 curl for math BSE allows us to define a fluid velocity potential, often called spal BFE.
So the fluid velocity math BFE is just the negative gradient of this math BFE.
Precisely. The fluid flows downhill on the psi landscape.
Okay, so you have math BFE from irrotational flow, and you have nabla math BFE from incompressibility. What happens when you combine those?
Pure mathematical beauty. You substitute one into the other, and you find that the velocity potential feat must satisfy Laplace's equation. Nabla psi equals 0.
Wow. So the potential for ideal fluid flow follows the exact same rule as the electrostatic potential in empty space.
Correct. And the application for visualization is just stunning.
Like the sphere example.
Yes.
Yeah.
Calculate the velocity potential C for an ideal fluid flowing smoothly past a solid sphere. You get a specific mathematical pattern for BC and the streamlines the paths the fluid particles take. That pattern is mathematically identical to the electrostatic potential Euler and the electric field lines math BFE you'd find if you placed a dielectric sphere, an insulating sphere, inside a uniform external electric field.
So looking at water flowing around a ball tells you how electric fields behave around an insulator.
Visually, yes. It really forces you to think about how much the underlying structure of space and gradients dictates the outcome, regardless of whether it's water molecules or electric force fields doing the interacting.
That's pretty profound. Okay, one last analog to tie things together. Illumination. Actual light.
Right, like radiant energy hitting a surface.
Uh-huh.
Let's think about the illumination intensity, $1, the power per unit area.
Okay.
If you have a simple point source of light, how does the illumination intensity decrease as you get farther away?
It follows the inverse square law, right? Double the distance, quarter the intensity.
Exactly. And what else follows an inverse square law from a point source?
The electric field strength from a point charge.
Bingo. That fundamental geometric similarity, the inverse square relationship, means that all the clever mathematical tricks and techniques physicists developed for calculating electric fields from complicated arrangements of charges.
To be used directly for designing lighting systems?
Precisely. Feynman gives the example of engineering uniform illumination. Say you want the light hitting the desks in a room to be perfectly even. You might have long fluorescent tube lights on the ceiling.
How do you space them?
Well, you can model each tube light as analogous to a long line of electric charge. You then use the established electrostatic methods for calculating the field from an array of charged lines to figure out the optimal spacing between the fluorescent tubes to get that uniform illumination down below.
That's incredibly practical, using E&M math to design lighting.
It really brings it home. Okay, so we've seen this same math, Poisson or Laplace, show up in electrostatics, heat flow, membrane mechanics, neutron diffusion, ideal fluid flow, and illumination. It's everywhere. Which brings us, as you said, to the kind of philosophical wrap-up Feynman touches on. What does all this sameness actually mean?
Right. Is it hinting that temperature, potential, membrane displacement, neutron density, are they somehow fundamentally the same thing deep down?
It feels a bit like the universe is just reusing the same lines of code over and over.
That's a good way to put it.
Yeah.
Feynman's perspective, though, is a bit more nuanced. He suggests the similarity isn't necessarily because the physical stuff, heat, energy versus electric field, is identical.
Okay.
Instead, the unity comes from the mathematical structure forced upon these phenomena by the underlying physical laws they all obey.
Which laws?
Primarily two types. First, some kind of conservation principle, like conservation of energy for heat or Gauss's law relating field flux to charge. Second, a relationship where the flow or flux is proportional to the gradient of some potential, like heat flowing down a temperature gradient or E field pointing down the voltage gradient.
Ah, so because they all follow those general rules, the resulting spatial distribution, the mathematical description of the field or potential, has to take the form of the Poisson or the plus equation. The laws themselves impose that shared mathematical structure.
So it's more about the universal rules of how things distribute and flow in space, rather than the microscopic nature of the things themselves.
That seems to be the main idea. It's a property of the differential equations governing these fields.
Makes sense.
Though it is important, as Feynman notes, to remember these are classical field theories. They work incredibly well on macroscopic scales. But modern physics, quantum mechanics and relativity, they show that at very small scales or very high energies, these smooth field analogies start to break down or need modification. The mathematical unity is powerful, but perhaps not the absolute final story.
Understood. Still, this deep dive has really highlighted an incredible shortcut in learning classical physics. If you, the listener, can really master the mathematical logic behind the Poisson equation in electrostatics,
You've simultaneously gained a massive head start on understanding problems in thermodynamics, mechanics, nuclear physics, fluid dynamics.
and even practical optics and illumination, it's all connected.
It truly demonstrates the power of generalized knowledge. Physics is deeply interconnected, and mastering the core mathematical tools of one area really does unlock insights across many others. It makes learning much more efficient.
Absolutely.
Mhm.
Which I think leaves us with a pretty fascinating final thought to chew on, inspired by that fluid dynamics analogy.
If the complex behavior of an electric field interacting with, say, a dielectric sphere can be perfectly mirrored mathematically by something as seemingly different as incompressible water flowing past a solid sphere,
Yeah.
then how much of the reality we observe is actually determined by the specific materials involved, and how much is just an unavoidable consequence of the fundamental mathematical rules that govern gradients, flows, and sources within space itself?
Is reality the stuff, or the rules this stuff follows?
Something to ponder until our next deep dive.